last time we were doing some trig identities, and we mostly just focused on proving the Pythagorean identities. We showed using the unit circle that sine squared x plus cosine squared x equals 1, and from there we were able to determine the other Pythagorean identities, like if we subtracted cosine squared x from both sides, we got sine squared x equals 1 minus cosine squared x, and vice versa. If I wanted to create a cosecant of x, I would simply divide everything by sine squared x, and that gave me 1 plus cotangent squared x, and blah, blah, blah. All the other Pythagorean identities kind of fell into place. So remember, I told you the only real identity that you needed to remember was sine squared x plus cosine squared x equals 1. Sometimes you see it presented as sine squared theta plus cosine squared theta equals 1. In these even-odd identities, I kind of switched out the x for the theta. And as long as you understand the fundamentals of each graph, how sine is an odd function, if you have sine of negative theta, it's basically the same thing as flipping sine of theta upside down. Cosine of negative theta is the same thing as cosine of theta because cosine is an even function, and then tangent's an odd function, so it's similar to sine. So when we are using these, we are actually going to be using these to verify trig identities. And to verify a trig identity, we're basically trying to prove that one side equals the other side. And so with this comes a couple of different things. One, you have to learn how to improvise really, really well. There's not really a set formula to it. You have to kind of feel your way through and kind of improvise as you go along. If you're paying attention in class, sometimes I make reference to this being similar to martial arts like Tai Chi or Wing Chun, when you have to improvise and feel your way through rather than going in with a set formula. A fight situation is not going to handle itself like a set formula, so you have to learn how to adapt. Trig identities are almost exactly the same thing, except a little less painful. So I'm going to just throw in some examples, and after about 1,000 of these, as one of my martial arts instructors has said, after about 1,000 of these, you will learn how to do them. Something will just click, kind of like in Wing Chun, learning how to punch with your elbow is really, really difficult, but after about 1,000, it starts to sink in a little better. Not that I'm a master or anything. Okay, so there are a couple of things you got to keep in mind. One, this side here, sine theta, secant theta, cotangent theta equals 1. This is true. It is going to work itself out, but you need to show some work to prove that this complicated side is equal to this simple side. Now, when you're working with trig identities, the one thing you have to remember is that you always have to work with the more complicated side, because the more complicated side gives you more things to work with. In class, I refer to this as a person who's throwing a bunch of flailing punches at you. This left side here. If they're throwing a bunch of flailing punches at you, the minute you make contact with one of them, you can feel your way through and then get him into a disabling, into somewhere where he can be disabled. Just like a trig identity, they're throwing a bunch of random trig functions at you. You can block, you can parry, and then eventually get this thing in a situation where this side equals 1. So let's see how this works. Secant. Well, secant, if you don't remember, secant is really 1 over cosine of theta, right? That's what secant really is. Now, sine I can't really do a whole lot with, so I'll just kind of carry it down. Remember, they're all being multiplied. Well, cotangent is really cosine theta over sine theta, and that equals 1. Well, since everything is being multiplied, we can suddenly start canceling things out. If you notice, the cosine thetas are going to go away, the sine thetas are going to go away, and you end up with 1 equals 1. And that's your trig identity right there. All right. Again, trig identities are a strong test of your algebraic manipulation skills, as well as your ability to adapt and to think quickly. And so it just takes practice. You really just have to do 1,000 of them before things become a little more clear. And so we're just going to do a bunch of examples. In this next example here, both sides kind of look complicated, but it's up to you to decide which side you want to work with. And with trig identities, one thing I forgot to mention is you only want to work with one side. Right? You really want to just stick to one side and make sure that one side equals the other. And so Personally, I feel that this side here, this left side, is more complicated than the right side because I've got a 1 here, I've got a negative cosine squared. I mean, I could change this into sine squared x using a Pythagorean identity. It's not really going to get me anywhere. So instead, I'm going to mess with this side because tangent is something a little more complicated than just tangent. Tangent is really sine squared x over cosine squared x times cosine squared x, and that's going to equal 1 minus cosine squared x. Well, similar to number 1 here, the cosines are being multiplied, so they're going to cancel each other out. So you get sine squared x equals 1 minus cosine squared x. Now, if you look towards your Pythagorean identities worksheet, or Pythagorean identities reference chart here, sine squared x does in fact equal 1 minus cosine squared x, so you can say that sine squared x equals sine squared x. Alright, let's do another one. Let's make it a little more difficult. Let's see, cosecant of x times secant of x equals cotangent of x plus tangent of x. Now, a lot of people tend to wonder, whoops, that's leftovers from the last lesson. People tend to ask, well, how can I determine what's the more complicated side? I mean, I got two things here that are really 1 over something else equals two things here that are really 1 over something else. Well, if I've got a bunch of 1 over something else's or a bunch of otherwise fractions here, the more complicated side presents itself in such a way where working with one side is going to be more difficult. And since I have a bunch of fractions here, and this side of fractions is being multiplied and the right side is being added, the right side is the more complicated side because, as hopefully you should know, adding and subtracting fractions is a lot more complicated than multiplying them. You need common denominators and blah, blah, blah. It's just a pain in the neck. So you want to work with the pain in the neck side. So I'm going to go ahead and transform this, for lack of a better word. Cotangent is cosine x over sine x plus sine x over cosine x. And don't forget, all that equals cosecant x times secant x. All right, so let's go ahead and find a common denominator here. The common denominator between these two is sine x cosine x, right? And I'm just multiply the two together. Now, in order to get the common denominator, I had to multiply by what's missing. So here needed a, oops, not a cosine, it's what it had. It needs a sine x. The left side needs a cosine x, right? Because we needed a cosine x down here to make it cosine sine, and then sine x down here to make it cosine sine. So what I've got here is I've got cosine x times cosine x. That is cosine squared x plus sine squared x. And from our Pythagorean identities, we know that cosine squared x plus sine squared x equals 1. And so what I've got here is I've got cosecant x times secant x equals 1 over sine x cosine x. Now from here I'm going to go ahead and do an algebraic split. Because I have 1 over 2 separate denominators being multiplied, I can say that it's really 1 over sine x times 1 over cosine x. Now, if you're not sure about what happened there, 1 times 1 equals 1. Sine x times cosine x equals the common denominator. And don't forget, all of this stuff equaled cosecant x and secant x. Well, 1 over sine x, well, that's cosecant x. Times, well, 1 over cosine is really secant x. And there you have it. And again, I have a funny feeling that some of you guys are confused. It's no big deal. Took me a long time to figure out how to use my elbow more when I'm punching, and I still think I'm struggling with it. And you will get better. So let me load up the next problem. Okay, wow, this is a bear right here. And so it doesn't take a rocket scientist to figure out what the more complicated side is. However, there's a couple of traps in this problem. One, I do not want you to think that 1 plus tangent x is a Pythagorean identity. Tan squared x plus 1 equals secant squared x, but because the tangent's not being squared, you can't convert it to anything. So we got to brute force this thing a little bit. Let's just change everything in terms of sine and cosine and see what happens. The top is 1 over secant, oops, not 1 over secant, 1 over cosine x plus 1 over sine x all over 1 plus, well, tangent is sine x over cosine x. And don't forget, all that equals cosecant. Okay, so let's take this one half at a time. I'm going to go ahead and find the common denominator up top here. That is going to be, just like in the last problem, sine x, cosine x. So I'm going to go ahead and multiply the right side by sine x. The right is going to get multiplied by cosine x. And so what I have for the top now is I have sine x plus cosine x, right? If I multiply those in, all over sine x times cosine x. Let's take care of the bottom. My common denominator here is cosine x. Right? So 1 just needs a cosine x up top and bottom. And that's supposed to be cosine x. So what I get is I should get, not that, cosine x plus sine x over cosine x. Right? Common denominator here, this is really 1 over 1 gets multiplied in cosine x plus sine x over common denominator cosine x. And let's not forget all that equals cosecant x. Okay. From here, what I can do is I can back this thing up to the top and flip it, because in a complex fraction, it's the top fraction being multiplied by the reciprocal of the bottom fraction. Okay, so now what do I got here? I've got a cosine x plus a sine x up top, and a cosine x plus sine x on bottom. They can cancel each other out. I've got, and you know what? Now that I've moved this thing up top, let's go ahead and delete it so we don't get confused. And now cosine x and cosine x can go away. The only thing that hasn't been messed with is the sine x, and that's 1 over sine x equals cosecant x. And what do you know? 1 over sine x is, in fact, cosecant x. Oops. All right, let's do a couple more. Hold on. This next problem, number 6, 1 minus 2 cosine squared x over sine x cosine x equals tangent of x minus cotangent of x. So again, it seems as though this side on the left is more complicated. It's got more stuff going on. There are 3 functions. However, because they're already over a common denominator and these are not, the right side is going to be easier to work with, at least in my opinion. So let's go ahead and make this more complicated looking. This is really sine x over cosine x minus cosine x over sine x. And that all equals this thing. Okay, I'm going to find a common denominator on the right side here. So a common denominator on the right is going to be cosine x sine x. So what I need on the right is I need a cosine x. And what I need on the left is a sine x. Oops. Never leave myself enough space on the left. But hopefully you can follow this enough by now where you can figure out that these two multiplied together give me sine squared x minus cosine squared x all over the common denominator, which is sine x cosine x, equals 1 minus 2 cosine squared x, oopsie, over sine x cosine x. So it looks like we're almost there. I mean, our denominators certainly equal each other, but our numerators don't quite do it. Now, this is actually kind of a neat problem because this is actually delving into something called a double angle formula. These two statements are actually equivalent, and I'll show you how. Let me just clear some junk down here. Okay, well, let's take a look at the top. I've got 1 minus 2 cosine squared x's. Well, I have 2 cosine squared x's on this side, on the left. I only have 1 on the right, so I need to figure out a way to create another cosine squared x. It's a good thing I've got this sine squared x right here, and I can refer back to my Pythagorean identity right here and say that sine squared x equals 1 minus cosine squared x. So I'm going to convert sine squared x into 1 minus cosine squared x minus cosine squared x all over the common denominator. And now I've got negative cosine squared x minus another cosine squared x. Let me just erase some more junk down here. Negative cosine squared x minus another cosine squared x is negative 2 cosine squared x's, and the 1 kind of comes down, and you have sine x cosine x, and that's going to equal 1 minus 2 cosine squared x over sine x cosine x. Okay, that is enough for now. I really think I have not covered the full Shazam of trig identities, but as long as you stay fluid and be like water, that's what Bruce Lee used to say, you should have relatively no problem, but we will do more examples. See ya.